Hello and welcome to this lecture. In this lecture, I'm going to show you some applications where the algebra involving matrices will show up naturally. So you might be wondering, are these topics just very abstract thinking, or does it happen actually? Okay, so I'm going to show you some simple example. We'll start with the communications example. A lot of linear algebra is used in communications and signal processing. I'll show you one example of why that is coming up. So here's the setting. It's very common. It's called a MIMO setting, multiple input, multiple output. You might have seen in your own house, if you have a Wi-Fi access point, it has multiple antenna things, and even your phone today has multiple antennas. The base stations have multiple antennas. So a lot of multiple antenna transmission happens today. So here's a very simple example of how that may look. Okay, so you have a transmitter. It is putting out a signal X, let's say, which is in RM. Okay, this is very common. And this m equals 4 is what I've used here, but generally it could be m antennas, and each coordinate of x will go into a particular antenna and it will get transmitted. Okay, so this is how we picture this. And now on the receiver side, there may be n antennas. I've shown n equals 6 here, but you may have n antennas. And every signal from every antenna here will make it to every antenna here. Okay, so you will have a gain from the ith TX antenna to the jth RX antenna. So by the way, TX and RX are standard short form for transmitter and receiver. Okay, so that's why I've written it like that. So you'll have a gain from the ith transmit antenna to the jth receive antenna. You can collect all these gains together and make a matrix, and that will be a m cross n matrix, which I'll call H. H is a common terminology for this matrix. So what you have on the other side is Y, which is belongs to Rn. There are n values that are received. So m values are sent, n values are received, and you have to do some processing with it. So the equation here that we write typically is Y equals H transpose X plus NZ. So you can see this is because X is a column vector. It's got m columns here. So when you multiply this H, you have to do H transpose so that the transmitter goes into the receiver and you get Y. Okay. So think about why this is true. Okay. But it turns out, and because of electronics and non-zero temperature and other things, it's not just H transpose X that you receive here. Noise gets added to it. Okay, so you get a noise Z. Okay, and the Z is a noise that you can't control. You don't know what it is. It's not something you created. Nature created it, and you're just observing it. Okay, so Y equals H transpose X plus Z. Now this is a hugely important equation in all of signal processing. There are so many things you do. The starting point will be this. Okay, you want X, but then you don't see X. X gets multiplied by some matrix, some noise gets added. The noise getting added is pure evil, by the way. So the multiplication by H, linear algebra can help you. Because of this noise, there will be a fundamental limit. You can't do too much, and that plays a crucial role. So this model, it's called, you can call it various things, basically linear model, Y equals AX plus Z, AX plus noise. This is a received vector equals matrix times transmit vector plus noise, and you have to figure out what the transmit vector is. This shows up in various different forms. So how does one approach this? How do you recover X plus Y from Y? That's the basic fundamental problem, and the trick is to do like this. In most of the receivers, one thinks of a matrix R, and you multiply R on the left to Y. Okay, Y is a column vector of 1, and you multiply by a matrix R. Now what does that do? It multiplies a right hand side also by R, so you get R H transpose X plus RZ. So notice how the algebra of vectors and matrices are entering into an application, right? So everything you do ends up being a matrix multiplication, vector addition, okay, naturally. I mean, you don't have to struggle too hard, okay. Now I want to find a matrix R such that this guy is close to X, okay. So now a couple of constraints here become very important. The first one is, to make this close to X, I should have R times H transpose becoming close to your identity, right? So that's a reasonable thing. So maybe that is something you can aim for. But importantly, even if you make this identity, this R times Z should not blow up. You should not do something crazy to push this H transpose to R times H transpose identity. You should not be doing something that is too crazy, because if you do that, then your noise will blow up. Okay, the noise which was maybe small or at some level, because you multiplied by this R, the noise should not go up. So this R should not have too many big values that will multiply the noise and blow it up. Okay, so how to find this R and all? You can imagine algebra will play a hugely important role here. So how does multiplication work? How does it impact H transpose? At the same time, how does it not impact Z, right? So the statistics of the noise will play a role, and the linear algebra part of it will play a role. Okay, so hopefully you see MIMO communications is all about matrices. In fact, instead of transmitting X directly, whatever you want to send, in fact, people do a pre-coding. So they'll multiply something with X first and then let the H handle it, and they'll do some filtering on the other side. So you'll multiply by another matrix here like R, and then you'll see all that, and that becomes very, very interesting. Okay, so that's communications application for you. So here is a completely different application where matrix algebra shows up from nowhere. Okay, so you will not see any obvious operational gain or noise that is adding and multiplying, right? That's where you expect matrix algebra to come in. Here is some other abstract problem where matrix algebra came out from nowhere. In fact, it's sometimes called the Netflix problem, right? So this is all trademark of Netflix. Okay, this is what is called ratings matrix completion. Okay, so it's a very interesting problem. So here is a problem that you might have seen in Netflix, or it need not be even movies and users, right? It can even be a retail chain which is putting out a lot of products and a lot of users are trying to rate it. Anytime you have ratings of anything by users, you have a matrix like this. Okay, so let's think of the Netflix example. So Netflix has thousands of movies. So n is thousands, movie 1 to movie n. And it has millions of users. Even in India, I think the users have crossed 12 million now, if not wrong. So it's a huge number of users Netflix has. So you have millions of users and thousands of movies. And each user, when they see a movie, they rate it. Okay, well, not always, right? So sometimes you rate, sometimes you don't rate. But if you rate it, the rating is available to Netflix. So Netflix has these ratings matrix, and Rij, I will say user i's rating of movie j, right? So that is the Rij. So you have a matrix naturally. At some level, this seems only a representational thing, right? So it is just an array of ratings that I am storing. Okay, ratings you can think of as integers or numbers from 0 to 5, right, or 0 to 10. Okay, it's a number. Okay, but it still seems like it is only a representational array of numbers. What is the meaning of? How do I think of the numbers as transformations, multiplication? Does it really enter? I mean, doesn't seem obvious at all that any sort of matrix algebra should enter this picture here. But one of the interesting points here is this R is clearly only partially known, right? There's no way every user is going to watch every movie and rate every movie. It's impossible, right? So it's not going to happen. Only some users are going to watch some movies, and only some of those are going to rate. Okay, and also it can be noisy, right? So you don't know. I mean, some people may rate very highly. There are people who will never rate any movie less than 3 out of 5, right? And there are people who will never rate any movie more than 2 out of 5. For them, everything is bad. And some people will only say everything is average. So a lot of characteristics of the people also enter into the rating. And sometimes they may genuinely make mistakes. They may see only one part of it, think it's great, put it off, and then go off. And then maybe the movie became very worse after that, all sorts of things are there. So maybe it's noisy, right? So you don't know. This noise also possible. Okay. So how does algebra enter here? So here is an interesting thing. See, R is only partially known. In fact, is very sparse. There's very few entries here are known. So the problem is, how do you complete the missing entries of R? Okay. See, a user has watched a bunch of movies. He has rated them, maybe rated a few of them, but he's not watched a bunch of other movies. So when Netflix wants to show you suggestions, it is trying to complete this matrix for you and say, okay, this guy watched this, he likes it, so maybe he will like this. It's showing you that, right? So how does it decide that? How does it decide what to show you? So it's what it does internally is a completing of this matrix. It has an algorithm which will run based on what is available. It will run that algorithm and complete this matrix, and that involves a lot of linear algebra, a lot of algebra with matrices. How does that happen? Here is how it happens. Remember, this R is a huge matrix, but I know only very small entries of it. So how do I complete? And here is where the trick comes in with the multiplication of matrices. Okay, so it's a brilliant trick, I think. Okay, so what you imagine is, you imagine that this big matrix R, even though it's very big, it is actually a product of two matrices. Okay, it's a product of a matrix A, which is M cross R, and then a matrix B, which is R cross N. And this R maybe is much, much smaller than N and M. Maybe it is just 10, right? Or maybe even 20, not more than that. Okay. So what happens now is this R matrix became the product of a very tall matrix and a very wide matrix. So you got a big matrix by the multiplication, but the number of unknowns in A and B are actually very, very small, because A and B themselves are sort of small matrices. So just with the known entries of R, you have some hope for finding the entries of A and B if the A is tall and B is wide. Okay. Now notice, because you are doing R being much smaller, what will be the rank of R, capital R? It will be less than or equal to small r, right? Assuming this A and B are full rank, it's going to be equal to R. So, and what you're assuming here is that this capital R, even though it's a big matrix, it's a low rank matrix. Okay, so this low rank matrix completion involves algebra of matrices, and it sort of comes from nowhere, right? So, where are movie ratings and where is linear algebra and multiplication? Okay, so you can see the fit. So, if you understand the underlying reason, so here one of the things people say of why this should happen is, when you rate a movie, what are you rating? You're probably rating the actors in the movie. You know some actor, you like them. Why do you watch a movie? You like some genre. So only some finite number of genres. So there are only a few factors you consider before you like the movie or not. So this R is like the number of factors that control the liking of a movie. And that is usually small. It's not like there's a huge number of factors for every movie. There's only a few factors that you do. And that is what is used in this low rank product idea. So this underlying notion of a low rank is very, very important. So how do you find A and B? You match known ratings, because the number of variables is very, very small. It's good, and we also don't want to blow up the noise. So you have to do things without blowing up the noise too much, and you can do that quite cleverly. Today there are very, very clever algorithms to do it, and some of those algorithms have been shown to be optimal and all that. So matrix completion is a powerful principle in showing how algebra of matrices can enter into completely unknown and unexpected places. Okay, the final application I want to show you, I'll go through this a little bit fast, but it's an important one because it proves as a direction to our next topic that we'll study. Okay, linear dynamical systems is again another area where linear algebra plays a huge role. Every single algorithm, every single method that's there in linear dynamical systems, like these drones, right? How do you control this quadruptor drones? I don't know, for four rotating things, quadriraptor, I think it's called, drones, and there's also a camera attached. So look at all the things you have to control, and it's a linear dynamical system. So it's a dynamical system because forces are applied on it, moves from time to time, with times its states changes. Linear dynamical systems have a time input, so everything is a function of time. These systems have a state. State could be, where it is, x, y, z position, and then how fast it's moving in each direction. Maybe all of this is state. Usually x and x will have a state like that. And then input. Input is what input you do from the remote control, right? So do you want to give it some force in some direction? You want to change the speeds a little bit? You want to tilt it a little bit so that it gets some drive and all that? All of those things are in the input. And output is where you desire the thing to be, right? So maybe there is some output that you're interested in at every state of the dynamical system, or maybe even the state it's the output. Output may be nothing. Okay, so a very typical assumption here is this kind of a model. Okay, so it's assumed that this is a model that's assumed all the time. And it's many cases it applies. Many physical dynamical systems obey these models. X dot of t. X dot of t is what? Is the derivative of x. X of t is a column, right? So it's a lot of values. Everything is a function of time. You take a derivative of everything, you get x dot of t. X dot of t is modeled as a times x of t plus b times u of t. So the input decides the rate of change of state. The input and the previous state, state at time t, decide the rate of change of state. And then the output is again c times x of t plus d times u of t. So A, B, C, D are matrices. So this is a very, very, very common model, a very powerful model. It models everything from very many things are modeled like this. Okay, so this is a model. Now a common thing that many people are interested in, maybe not in the drone or maybe even in the drone, you are interested in a case where x dot of t is 0, right? So the drone is stationary somewhere, right? So it's not moving anywhere. The position is stationary, the velocity is all 0 maybe, right? Or maybe it's constant velocity, whatever. So it's in some sort of a steady state, in which case x dot of t you expect to be 0. So you may put x dot of t is 0. So if you put x dot of t is 0, notice what happens here, a times x of t becomes b times u of t. So there's some algebra you can do here. You can now do division. Okay, so this division is a powerful idea. So what happens is, if you write a times x of t plus b times u of t is 0, it's the same as u of t, x of t becoming a inverse minus a inverse b u of t, right? So notice the algebra I'm doing this. A inverse, a goes on this side, so how do? You multiply by a inverse. So this motivates the use for inverse. So far we have not seen inverse. So it will be nice to have an inverse here, right? So because then you can write x of t as minus a inverse b u of t. X dot is 0, so you can do algebra here, just similar algebra. And then you plug in that x of t here, you get y of t is minus c a inverse b plus d into u of t. Okay, so notice how algebra enters the picture beautifully when you put in these kind of conditions. Okay, so this is a very common way in which steady state is described in linear dynamical systems, and you can see the inverse of a matrix enters the picture. Okay. So in fact, let me show you a more fancy equation. This is called the algebraic Riccati equation. I'm not going to describe where it comes from. It comes from something called optimal control and all that. It's a more complicated thing. But notice this equation. Okay. So a lot of control theory people who work on control try to solve this equation. Try to solve the Riccati equation. Look at how the algebra is. All these things are matrices of suitable dimension. There is transpose, there is inverse, and they all add up to 0. Okay. So that's how you solve this equation. Okay. So hopefully this tells you that inverse of matrices is important. If you can have inverse for matrices, you can do considerably better algebra. And we have seen 3 applications, all sorts of different ways in which matrices show up and how the algebra of the matrices impacts the application very, very directly. Okay, so from here we are going to pick up and study how to think of inverses of a matrix and inverse of a linear transformation. Okay, thank you very much.